There's a certain puzzle that's been stuck in the back of my mind for a while now, and by a while I mean a few years. It's not because the puzzle was some massive endeavor that took weeks to solve. It took me all of one summer's morning to work through it. It's not because the puzzle's gone unsolved for years or anything. I'm far from the only person who solved it. The reason I still think about this puzzle is because it was a fun puzzle to solve. It was a problem that left me with both a relatively satisfying understanding of some simplest geometry and a relatively satisfying process for arriving at said understanding. With this video, I want to walk you through my process for solving this particular puzzle. Now, maybe this video will be mildly interesting, or maybe it'll help you get better at solving geometry-type problems in the future, but honestly, my main goal with this video is solely to point out the parts of my process that I think are applicable for solving any problem, not just the one I'm interested in here. So often, at least for me, the thought of doing math or any sort of problem solving is daunting, sometimes even scary. I mean, other people seem so good at it. YouTube is flooded with people posing these monstrous problems, only to solve them effortlessly in about 12 minutes or less. I can't compete with that, can I? Of course, these videos can't possibly show all the time these people have spent studying or researching or banging their heads against a wall hoping for some spontaneous burst of insight. Everyone goes through this process, that much I'm sure of, but the fact that it's often hidden away can give the impression that problem solving is supposed to be clear, instantaneous, and, ironically enough, a problem-free process. This video aims to dismantle that view. First, I want to point out some common techniques used pretty much everywhere in math that almost certainly will come in handy if you ever decide to do some problem solving yourself. Second, I want to describe as closely as possible the train of thought I had while solving this puzzle, not only for posterity, but also to show the specific steps I took, no matter how slow or unnecessary. I don't want the process to be perfectly polished. I want it to be real as I can make a pre-scripted YouTube video anyway. So, what even is this magical puzzle that I've been hyping up so much? Well, I originally saw it on Twitter many years ago. I've searched for quite a while, but I can't seem to find the original post anymore. I don't remember who posted it, and I don't remember how I came across it. All I remember is that I saw it pretty much immediately after I woke up that morning, which caused me to spend the entirety of that morning working on it. Now, did the problem really require all that time? No, not really. I'm sure someone more well-versed in geometry could solve it in a few minutes. However, other than the odd analytical geometry problem, I'm not as fluent in this area as I'd maybe like to be. That didn't stop me from trying, though. And try I did. Like I said, this puzzle took me several hours to wrap my brain around. And you know what? Maybe that was a good thing. When I finally did get an answer, I compared what I got to all the replies under the tweet, as you do. My answer agreed with everyone else's, thankfully, but my method for solving it was completely different from what everyone else was doing. The common approach seemed to be to draw these triangles here, form a system of equations, and solve for a particular quantity. Now, I don't want to brag or anything, but my method for solving the puzzle is a teeny bit more satisfying than that. And it also provides insight into why the answer necessarily has to be the way it is. Though, all this comes at the cost of being a little more complicated than the other approach. I realize I still haven't described the problem. Okay, no more procrastinating. Here it is. We're given a square, like this one, let's say, along with some arbitrary point inside the square, maybe here. From the center of each of the square's edges, extend a line to this point. This divides the square into 4 regions. You can count them if you don't believe me. Here are the areas for 3 of these regions. What's the area of this 4th region? If you want to pause the video and give it a shot, go ahead. I don't mind, I promise. When you're ready, keep watching and I'll step through what I did to solve it. Alright, here we go. So, the first thing I did was, think. And think. And think some more. My initial instinct was to try and find the side length of the square. I mean, once we have the side length, we can find the entire area of the square, and finding the area of this single quadrant becomes a simple subtraction problem. Just take the total area and subtract the other 3 quadrants. However, no matter how hard I tried, I couldn't for the life of me find a way to get the side length. Really, most of my time spent on this problem was spent trying to get the side length. There's probably a way to get the side length, but I never found out how. And as it turns out, you don't actually need the side length anyway, so it wasn't that big of a loss. So, okay. At this point, I'm staring at a page filled with equations and expressions and random lines drawn over the square in the hopes of somehow squeezing out the side length. What do I do now? Well, I realized that, in its current form, the problem is just too difficult for me to solve. I need a foothold of sorts. I can't just solve it in its current form. I need a little bit of help. Thus, I decided to turn to one of math's most useful problem-solving tools, simplification. If a problem's too difficult, try solving an easier version of it. It usually helps set your mind in the right direction, pointing out the ideas that may be useful to consider on the harder problem. Pretty much every problem I've ever encountered in math has benefited in some way by considering an easier version first. Even when just learning to solve a particular type of equation, for example, it's often super handy to have a simpler reference equation in your head to help keep your mind focused on the important bits. Alright, cool. Sounds like a plan. Let's simplify the problem. So, how do I make this problem simpler? Well, wouldn't it be really nice if this arbitrary point was directly in the middle of a square? Then, all 4 quadrants would be identical mini-squares, meaning they'd all have the same area. Thus, the missing area would be exactly the same as the area of the other 3. Problem solved. That's good, I guess, but this seems a gross oversimplification. I mean, it's pretty obvious that our 4 quadrants are not, in fact, identical mini-squares. Not even close. This particular simplification doesn't really seem to help all that much. Okay, let's see what else we can do. Putting this point at a random place inside the square is way too difficult to work with, but putting it exactly at the center of the square is perfectly fine. Is there anywhere else we can move the point to keep the quadrant simple enough to manipulate? After looking at the square some more, I realized that, yeah, actually, there's a bunch of places where we can move the point and still make sense of the different areas. Imagine putting the point at any place along this line, the line that's perpendicular to the top edge of the square, and that passes through the center point. If we put the point on this line, each quadrant becomes either a square with an extra triangle, or a square with a triangular bite taken out of it. It's easy to see that the 2 halves of the square are symmetric, so if we know the areas of these 3 quadrants, we can still easily find the area of the 4th quadrant. One side is just the mirror image of the other, so we can just copy the areas. As well, if we were to instead place the point somewhere on this line, the line that's perpendicular to the left and right sides of the square, and that passes through the center point, we'd have the exact same situation, except the mirror line is horizontal, not vertical. We would still be able to copy the areas in this case, just drag it down, and there you go. Again, these particular situations are nice, but it's difficult to see how we could take these setups and somehow use them to figure out the general case where there isn't any symmetry. For the case we're concerned with, it's clear that there isn't any obvious symmetry between the quadrants. We can't just directly compare areas like we can in these simpler cases. However, as I was looking over these simpler cases, wondering if maybe there were other special lines I could place the point on to create some form of symmetry, I realized that there was another super useful problem-solving tool that was just begging to be used. Invariants. What's an invariant, you may ask? Well, inquisitive viewer, an invariant is something that doesn't change. It's a constant. Why would constants be useful? Well, let's use our current puzzle as an example. Our current approach to this puzzle has a lot of moving parts to keep track of. We have this movable point, we have the dividing lines between the quadrants, we have the areas of each quadrant, etc. As we mess around with the puzzle, these values are constantly changing. It's difficult for us to make sense of them since every different arrangement of our puzzle causes these values to change. With an invariant, however, we wouldn't need to worry about this. No matter how we change our puzzle's arrangement, an invariant would remain the same, just by definition. Because of this, it may be easier to make sense of our puzzle in terms of an invariant rather than all these changing values. Alright, so that's cool, but if we want to somehow make use of invariants, we need to actually find some invariants first. Well, there's one invariant that's been staring back at us this entire time, the area of the square. Sure, the problem might not give us the exact area of the square, but we know that no matter where we move this point, as long as we keep it inside the square's area has to remain fixed. We're not adding or subtracting any area by moving this point, we're merely changing how the square is cut up. Despite what certain chocolate bar cutting tutorials may lead you to believe, cutting up a rectangle in a particular way, with a finite number of cuts anyway, is not going to magically add more area to the original rectangle. So, we can be sure that the area of our square is an invariant. Along with the total area of the square, in the 2 symmetric cases we looked at, you might already be able to see another invariant. So long as we keep our point on one of the 2 quote-unquote easy lines, the 2 halves of the square remain the same area. My mouse is a little shaky, but just imagine I'm dragging the point straight across the line so that the 2 half rectangles stay the same. Therefore, the area of these symmetric halves of the square are also invariant. On top of these 2 invariants, there's actually a third invariant here that's a little more subtle, and it's also the invariant that proves to be the most useful. Instead of looking at all the quadrants, let's only focus on these 2 opposite sections. It's a little harder to see than our other 2 invariants, but if we move our point along one of our 2 quote-unquote easy lines like before, the area of these 2 quadrants together actually stays constant. For example, if we move our point here, the area gained by this quadrant, represented by this colored triangle, is exactly the same as the area lost by this quadrant, represented by this second colored triangle. The triangles have the same area by virtue of them having the same base, which is half the side length of the large square, and the same height, however far along the easy line our point is. However much area one quadrant gains, the other loses, because the two triangles are the same, so there isn't actually a change in our total area here. It stays constant. Along these particular easy lines, the area of opposite corner quadrants is invariant. I found this fact pretty interesting when I first found it. I found it so interesting, in fact, that I tried to force it to work for points off of our two easy lines. I mean, can you blame me? If this fact was somehow true for any arbitrary point we chose in the square, then that would mean that the area of these two quadrants, which is half of the large square's area, would be exactly the same as the area of these two quadrants, and these two, etc., etc. No matter where we'd move the point, the area of these two quadrants put together would stay the same. The area gained by one would be lost by the other. We'd be able to immediately find half the square's area, which would then allow us to find the entire square's area, which would allow us to find the area of this little quadrant, which has caused us so much headache up to now. Well, guess what? Sometimes the universe plays nice. It turns out that the area of opposite corner quadrants actually is invariant, no matter where we place this interior point. As different as all these areas may look, they're actually exactly the same. How did I figure this out? By drawing some more lines, of course. Well, line, singular. If we draw a line from the center point, the actual center point, to our interior point here, then we can draw some more triangles and see that the two areas added together really do remain constant. The triangles we have to draw are pretty simple. The sides of the triangles consist of this new inner line we've drawn, a side of the quadrant that's inside the large square, and the quote-unquote original side of the quadrant, what the side would have looked like had our point been in the center of the square. So basically, the side of the original mini-squares we were dealing with. Here, it's much easier to visually see these triangles rather than try to describe them. For this quadrant, here's the first triangle, and here's the second. You can see they just kind of fit into place. For this quadrant, the first triangle goes here, while the second goes here. Basically, the triangles represent the changes made from the original mini-squares to whatever quadrants we end up with. As I move the center point, watch how the triangles change. As you can see, those triangles are a sort of representation for how much the quadrant has deviated from its original mini-square form. Using these triangles, it's actually a pretty straightforward argument for showing that the area of the opposite corner quadrant stays the same. All we need to show is that the change of area to one quadrant is equal to the negative of the change of area to the other. In other words, the area gained by one quadrant has to equal the area lost by the other, just like before. If this is true, then there's no way their areas added together could ever change. If the area of one goes up, the area of the other goes down by the exact amount needed to keep the sum of their areas constant. That's what it means for these areas together to be invariant. To prove that this is actually true, there are two cases we need to consider. The first is when one quadrant has both its triangles inside its mini-square, like this, while the other has both its triangles on the outside. Here, we can easily show that the area lost by this quadrant is equal to the area gained by the other simply by comparing their triangles. These two triangles have the same area since they have the same base and same height. Similarly, these two triangles have the same base and same height, so they're also equal in area. Therefore, these two triangles added together have the same area as these two triangles added together. So the area this quadrant loses is equivalent to the area this quadrant gains. The second case we need to look at is when the two triangles for each quadrant intersect a bit, like this. If we're not dealing with the first case, then this is the only other case that can happen. I'll leave it to you to verify that this is actually true. It's a good way to test yourself if you want to do some problem solving of your own. Anyway, when the two triangles for each quadrant intersect like this, it's helpful to write everything out more explicitly. The total change in area of this quadrant from this to this is the area of this triangle minus the area of this triangle. Notice that when we add this triangle, we're actually adding a little bit more to the square than we should. This extra bit isn't in our quadrant. This is actually okay, however, since when we subtract this triangle's area, we're getting rid of that extra bit, which happens to be the exact area where the two triangles overlap. Similarly, the total change in area of the other quadrant from this to this is the area of this triangle minus the area of this triangle. Now, if we play the same triangle comparison game as before, we see that the areas of these two triangles are the same, and the areas of these two triangles are the same. If we write the changes in area in terms of only the green triangles, we see that the change in area for one quadrant is the negative of the change for the other quadrant. When you swap the order of subtraction like this, all it does is change the answer from positive to negative, or vice versa. This is great news! Since the changes in area are additive inverses of each other, one is the negative of the other, it means that the area gained by one quadrant must be lost by the other. This is exactly what we wanted to happen. So, in both cases, the area added to one quadrant is lost by the other. Therefore, we can confidently say that the area of opposite corner quadrants is invariant, no matter where we move our interior point. And if you wanted, you could make this exact argument for the other pair of opposite corners as well. Almost nothing would change since these two quadrants are just the mirror of the quadrants we worked with. Our entire process would be exactly the same, just with opposite corners. So, taking a step back to the original problem, we can now approach it using our newfound invariant. We know that this area plus this area is the exact same as this area plus this area, because opposite corner quadrants are invariant. So we know that this area is equal to half of the large square. So the total area of the large square is 2 times, 32 plus 16, which is 96. Now, to find the area of this rascal, we just take the area of the total square and subtract the other bits, leaving our area of interest. So, 96 minus 20 minus 32 minus 16 equals 28. And finally, we know the area of our missing quadrant. It's 28. Alright, well that was a little long-winded, but we got there in the end. The cool thing about our approach is that we could be given any 3 random quadrants of a square and immediately be able to find the 4th just by doing some adding and subtracting. Our invariant is true no matter how the 4 quadrants are shaped, so long as they're cut how the problem specified, of course. So our process for solving this problem would be exactly the same, even if the numbers were different. What's important about our solution, however, isn't really what it allows us to do, but rather the friends we made along the experience we gained along the way. Using invariants to approach problems is a super common trick. Many problems become much easier when you stop focusing on the chaos and focus on what remains constant. In a sense, invariants provide a sort of intrinsic look into a problem. No matter how crazy things may get, these problems always hold on to these invariants. In our case, the opposite corner quadrant invariance, that's a mouthful, was essentially all we needed to describe the complexities of the areas changing inside the square. The invariants provided structure for us. Chances are, invariants will provide structure for future problems as well, not just this one. It's also important not to forget how we found the invariants in the first place. If we hadn't looked at simpler versions of the problem, we may never have clued into this invariance. Simplifying the problem in the way we did revealed certain patterns and symmetries that, while not directly applicable to the more complicated case, set us in the right direction looking for properties of the puzzle we could make use of. Again, simplifying problems will often do this. This random square puzzle is not the only place where simplifying comes in handy. Finally, we never would have even been able to solve the problem unless we had patience. Math videos, including this one, are really good at pointing out the types of strategies and techniques helpful for solving problems. However, when approaching most problems, it's not entirely obvious which strategies to use, if any. The only way to figure that out is through patience. Answers don't come immediately, they take time. Don't be discouraged if you can't work through a puzzle as quickly as some random person on the internet. Chances are that it took them just as long to solve it, if not longer. Of course, you don't see this, because sitting around throwing ideas at a wall isn't really the most interesting YouTube content. Oftentimes that part of the problem-solving process is cut out for time. I tried to include it in this video as much as I could, but if I really wanted to show you the full, unedited problem-solving experience, this video would be several hours long, and I'd rather not make a video that long. Hopefully you understand. So yeah, that was my Summer of Math Exposition 3 submission. I hope you learned something, and I hope you had fun while doing so. That is all. Goodbye.